Welcome back, everybody, for another deep dive. This time, we're going to be looking at something that might seem a little abstract at first, but believe me, it gets really interesting. We're going to try to understand the world of rational and irrational numbers. And to do that, we're taking inspiration from a very unexpected source, pigeons.
Pigeons. That's not something you hear every day in a math discussion.
I know, right? We're looking at a YouTube video from the channel Tem Ciencia. And the title is O que pombos tem a ver com funho a representação de números, which translates to, what do pigeons have to do with the representation of numbers?
Okay, now I'm interested. This doesn't sound like your typical math lecture.
Not at all. So let's start with the basics. Rational numbers, those are the ones we all know and love, right? Fractions, decimals that end or repeat in a pattern, they all fit under that category.
Yeah, exactly. The basic idea is pretty simple. Any number that can be written as a fraction where the top and bottom numbers are integers, that's a rational number.
Okay, that makes sense. But here's where I always get a little confused. Pi, for example, it's the ratio of a circle's circumference to its diameter, but it's irrational. Why is that?
That's a great question, and it shows a common misunderstanding. While pi is a ratio, the key is that both the circumference and diameter can't be integers at the same time. So you can't accurately write it as a fraction of two whole numbers, and that makes it irrational.
So it all comes down to whether or not we can express it as a precise fraction. Got it. But how can we tell if a number is rational or irrational just by looking at it?
Decimal representations are key. Rational numbers always have decimals that either terminate, which means they have a clear endpoint like 0.25, or they repeat in a predictable pattern like 0.3333, and so on.
Okay, so those repeating decimals, no matter how crazy the pattern might seem, they can always be converted back into a fraction, which proves they're rational.
Exactly. Now, this is where the pigeons come in. They won't be solving equations or anything, but they illustrate a really cool mathematical principle that helps us understand the difference between rational and irrational numbers even better.
All right, I'm ready. Bring on the pigeons.
It's called the pigeonhole principle. It's incredibly simple, but really powerful. Imagine you have some pigeonholes and you have more pigeons than pigeonholes. If you try to put every single pigeon into a pigeonhole, at least one of the holes is going to have more than one pigeon.
Okay, that makes sense. It's like trying to fit 10 people into 9 hotel rooms. Someone's got to double up.
Exactly. And this principle, it may sound basic, but it's used in all sorts of areas like computer science and probability. It shows how ideas that seem totally different can actually be connected in surprising ways.
Okay. I can see how this simple principle could be more important than it seems. But how does it apply to something as abstract as numbers?
Well, for that, we need to take a closer look at division. Specifically when we're talking about fractions. Remember, rational numbers can always be written as fractions.
Okay, so we're diving into division to connect this pigeonhole principle to rational and irrational numbers. I'm honestly a little lost. How do those two things relate?
It's all about the remainders you get. When you divide two integers to get the decimal representation of a fraction, the possible remainders you can get are limited by the denominator.
Okay, so if we're dividing, let's say, 7 by 3, the only possible remainders are 0, 1, or 2, right?
Exactly. And those remainders become our pigeonholes. Now, think about each step you take in that long division process as a pigeon.
So as we keep dividing, we keep getting more and more pigeons or steps in the division.
Right. And if the decimal representation of that fraction goes on forever, eventually you're going to have more pigeons than you have pigeonholes.
So that means the remainder has to repeat at some point. Just like with the pigeons, you can't keep putting them in a limited number of holes without eventually doubling up.
That's the pigeonhole principle in action, and that's how we know that an infinite decimal that doesn't repeat has to be irrational.
Wait, so you're saying if a decimal goes on forever but doesn't repeat, it can't be a rational number because it would break the pigeonhole principle.
Exactly. That's the really cool connection here. A repeating decimal means you hit a remainder you've seen before, and that forces the pattern to repeat. But with irrational numbers, those decimals just keep going and going without ever repeating.
Wow, that's a pretty elegant way to show the difference between those types of numbers. So any number that can't be written as a nice, simple fraction breaks this pigeonhole principle when you look at its decimal form. That's amazing.
It is. It shows how interconnected all these mathematical concepts can be, even if they seem totally different at first.
This whole deep dive is mind-blowing.
Okay.
So rational numbers, they fit neatly into their little fraction boxes. And then irrational numbers, they're like rebels breaking the pigeonhole principle with their never-ending, non-repeating decimals.
I like that. And this actually brings up another interesting point. if irrational numbers can't be written as simple fractions, how do we actually work with them in math? They show up everywhere, from geometry to physics.
Yeah, that's a good question. Do we just kind of shrug and say too complicated?
Not quite. We can't write them exactly as fractions, but we have ways to approximate them with different levels of precision.
So basically we're using really close estimates.
Yeah, for practical purposes, you could say that. Think about pi, for example, one of the most famous irrational numbers. Usually we just use 3.14 or maybe 3.14159, depending on how accurate we need to be.
Right. And those are close enough for most things.
Exactly.
Yeah.
That's how we manage to use these fascinating, slightly mysterious numbers in all sorts of fields.
So even though irrational numbers can't be perfectly represented as fractions, we've figured out how to work with them well enough to actually use them.
Exactly. And that ability to use these numbers, even if we have to approximate them, has led to some really amazing advancements in math and science.
This has been such an eye-opening deep dive. We started with pigeons and ended up talking about the nature of irrationality.
It just goes to show that being curious and wanting to explore can lead to some incredible insights. And, thinking about how we work with these irrational numbers makes me wonder about something else.
So we talked about how we approximate irrational numbers to actually use them, but what other interesting thoughts did you have?
Well, it makes me think about what it means that these numbers can't be written as fractions. Like, what if they didn't exist at all?
Huh. I never thought about it like that. What would a world without irrational numbers even look like?
Our understanding of math would be much smaller and honestly less interesting. Rational numbers are important with their neat fractions and all, but irrational numbers, they add a level of complexity and depth to math,
I see what you mean. They push the boundaries of what we can even express with numbers.
Right. Like, think about the square root of 2. It was one of the first irrational numbers that was discovered by the ancient Greeks, and it really messed with them. It challenged their understanding of geometry because they couldn't fit it into their system of rational numbers.
So discovering these irrational numbers was a big deal for math.
Totally. It forced mathematicians to think in new ways and develop new tools to work with these weird numbers. And that led to tons of other discoveries and advancements.
It's amazing how something that seems so abstract, like the difference between rational and irrational numbers, can actually change how we understand the world.
It really is. And it leads to a question that I find really interesting. Are all irrational numbers the same, or are there different types of irrationality?
Different types of irrationality. Now, that's a new one. What do you mean by that?
Well, we've been talking about how irrational numbers can't be written as fractions. But that makes me wonder, are some irrational numbers more irrational than others?
Whoa, that's a trippy thought. It feels like we're about to go down another rabbit hole of math mysteries.
Exactly. And that's where I'll leave you, dear listener, with this idea to think about. When you come across irrational numbers, think about what they really are. Are they all equally impossible to pin down as fractions, or is there a whole hierarchy of irrationality out there just waiting to be discovered?
I love that. We started with pigeons, then we explored repeating decimals, and now we're questioning the very essence of irrationality. Who knew that a simple YouTube video could lead to such an awesome exploration?
It just shows that curiosity can take us to some amazing places.
That's right. So to all our listeners out there, keep exploring, keep asking questions, and you never know what mathematical wonders you might find. Until next time, happy calculating.